your attention. Good morning, everybody. It's my great pleasure to start the ceremony today. Several of our Scholes Memorial Lecture. My name is Minoru. I'm a professor here in Material Science and Engineering. I'm the host of this event today. First of all, Dean Edwards and the Vice President of the New York City College of Ceramics, Doreen Edwards, could not be present at this function. She's sorry about that, but she sends all her best wishes. The first order of the event today is presenting the Scholes Scholar Award, which will be followed by the presentation of the speaker. Let's start with our proceedings. The first business is the Scholes Scholar Award. The Scholes Scholar Award was established to honor the late Dr. Samuel R. Scholes, who founded the glass technology program at the New York State College of Ceramics at Alfred University in 1932. Awarded for achieving the highest grade point average as a freshman, a ceramic engineering and material science student, this year this award goes to Mr. Peter Hoskins. I think we have Peter here. We also have Mr. and Mrs. Charles and Susan Hoskins, his parents, here. Let's first applaud this accomplishment. And our student advisor is Dr. Payton, who is also here in the audience. Let's thank the advisor as well. The award comes with a certificate and also your Barnes & Noble gift card for $250. I hope that's exciting. Okay, please. So let me present this to Peter. All right. Now comes the presentation, introduction of our speaker today. Before I do that, I wanted to let you know this is a historic Scholes lecture series, and as you may notice in the program, this has been going on since 1982. We do have two of the past Scholes lecturer here in the audience, which are Professor Jim Warner and Professor David Rossington here. And this year's speaker is Professor Tomozawa. Let me just introduce him with a few words, and you may see his biography in the program. I'm delighted to introduce him. Professor Tomozawa is a professor of material science and engineering at the Rensselaer Polytechnic Institute in Troy, New York. He's been teaching material science, conducting research on various aspects of glass science and engineering for the past 45 years. He has published over 287 papers on glasses, and the majority of the work concerns with water in glasses. You'll be surprised how he can show you can't actually put water in the glass structure and make it even do great things inside. He served as a co-editor of 4 volumes of collections of review articles on glass science, glass 1, 2, 3, and 4, over a period of time in series of material science and technology series published by Academic Press. Among many other his accomplishments, he has also published several specialized proceedings with Journal of Non-Crystalline Solids. Professor Tomozawa received his PhD degree in electrochemistry from Yokohama National University in Japan in 1961, and a PhD in metallurgy and material science from the University of Pennsylvania in 1968. Between 2 universities, he worked as a material engineer at Nippon Electric in Japan. At Rensselaer, he trained 46 graduate students, most of them are PhDs and 35 visiting scholars and several postdoctoral associates. He served as the Director of Glass Science and Technology at Rensselaer between 1985 to 1992. He received Outstanding Professor Award from School of Engineering of Rensselaer. He is a Fellow of the American Ceramic Society. He's also a former Chair of the Glass and Optical Materials Division of the ASRS. He received 1997 Outstanding Educator Award from the Ceramic Educational Council, and he's also winner of 2010 George Mori Award of Glass and Optical Materials Division. He has also received 1983 Science Award and 1991 International Consortium Award, both from the Ceramic Society of Japan. With that introduction, I welcome Professor Tomozawa to the campus, and also I invite him to the podium for the lecture.
Scholes Memorial Lecture. In case you didn't notice it, I still carry the Japanese accent of English after 50 years living in this country. I used to apologize for my accent, but some years ago I went to a international conference in Corsica, that's the territory of France, and on the mechanical properties of materials. First speaker was a Frenchman, a prominent metallurgist, and these days even Frenchman has to speak English in international conference. And first he said, I'll speak my English with French accent, and I'm proud of it, he said. So following his suit, I will not apologize for my Japanese English. Now, the topic of my talk is glass and water. I have been doing research on glasses nearly 50 years, 35 years of that on water in glass, and this is most likely to be my life work. This work is in collaboration with the professors in mechanical engineering and two graduate students, one in material science engineering, one in mechanical engineering. The first graduate student, Peter Lezzi, just finished his PhD, and beginning this month he's working at Corning Incorporated. Water and glass is my topic, and especially water in glass is my major research topic. And some years ago when I gave this talk, Water in Glass, I said limited number of people are interested in water in glass. One of the audience said, that's not true. Everybody is interested in water in glass, especially water contains a little bit of alcohol. So I decided not to say this shows the type of water I'm interested in this glass, while most people think the water in glass here. And there is an old saying in Japan I grew up with. It says, peach, chestnut 3 years, persimmon 8 years. What it means is it takes 3 years to a peach tree to bear fruits, and chestnut is 3 years. But there's a fruit called persimmon that takes 8 years. And what I feel is glass research 50 years. It takes 50 years. Hopefully, after nearly 50 years of research, I can show you some of my fruits. Water can be in glass, normally exists as impurity, and its existence can be detected by infrared spectroscopy, FTIR. And when a small amount of water in glass, infrared beam is absorbed, and that can be shown in this slide. This is the FTIR. This one is a little bit thicker specimen, few millimeter, and this peak absorbance, this peak and this small peak is due to water impurity. And the small amount of water in glass has a dramatic influence on various glass properties. If you make thinner sample, you can look at around here, and there are nice peaks. And this is the water band, and the rest of the peak is due to the structural band. And by looking both this one and those peaks, we found lots of interesting phenomena. And this work was done by those two graduate students. Davis happened to be Alfred undergraduate. He's one of the most careful experimenters. Many of my current research is the extension of what he has started. Agarwal, as name implies, is an Indian graduate student, and he is now a CEO of a fiber optics manufacturing company with a sales of $1 billion. So both of them were best students I have had, and we got this result. And from the peak position, very careful measurement, we found this peak as well as this peak moves with fictive temperature, and that position can be used to measure fictive temperature of glasses. That will come sometime later. Now, the water has a dramatic influence on many of glass properties, but normal glass contains water 0.1%. We wanted to investigate what happens if you put lots of water in glass. And this is the area geologists excel. They use high pressure vessels to incorporate large quantity of water. There are some natural glasses, volcanic made glasses contain large quantity of water. So first thing, some 20, 30 years ago, we measured property change with large quantity of water. This is the sodium silicate glass normal glass transition temperature, 460, 470, that range. And if you put water, it goes down, down, down. And we extrapolate 100% water, that would reach to the glass transition temperature of glass form of water. So water can be made into glass too. This one is the electrical conductivity, sodium diffusion constant in the similar glass as a function of water content. And the two lines, one is the diffusion coefficient of sodium measured by isotope tracer method, and the other was by measuring electric conductivity, knowing how many sodium in it, you can calculate the diffusion constant of the sodium, and they seem to agree with each other with experimental error. And it shows that small amount of addition of water dropped the diffusion constant tremendously. Before this work, some people reported the diffusion constant would increase with water content or decrease with water content. By measuring a large concentration of water effect, we can definitively say this is a trend. This is the hardness of glass. If you have a lot of water, glass becomes softer and softer. This is a new indentation hardness. Two glasses both are decreasing its hardness. This is a well-known optical attenuation by German scientists. This is the range where our telephone communication is used, here or here, 1300 or 1500, and there are large absorption due to water. If trace amount of water was included in optical fibers, you have large loss. This optical fiber made of this mass would not be useful. If you make it in a very carefully dry condition, you still have this water band. So optical fiber development was a battle against the water impurity. We found also that when you expose glass containing water, the glass doesn't color. Normally, glass you expose X-ray, high intensity X-ray or gamma ray, glass becomes dark brown or black. But we found with water containing glass, the coloration is very small, while this without water has a tremendous change in color. It's shown in terms of spectroscopy. Even if the glass doesn't contain water, if you measure some properties such as indentation hardness in air, then air or water, hardness goes down. Other non-aqueous solution, hardness does not change with time. So only when you have air or water goes down, down, down with time. This phenomenon is called indentation creep. Has been well known in the community, but what we found is that drop is due to the water entry. Water is entering into the glass while you are doing indentation work. And we show this by the infrared peak formation before and after indentation. And if you look more carefully, there's more water here than here. So definitely while you're measuring hardness, room temperature in air with a slight amount of moisture around, the hardness decreases with time. That's because water getting into the glass. From the peak position of infrared, as I mentioned earlier, we found that peak infrared structural band peak changed with heat treatment time and temperature. In these case figures, we showed first we hold the glass, silica glass at 1100 or 1300 long time until it reached metastable equilibrium, rapidly cool. So the fictive temperature of the initial glass was 13 and 11. Then both glasses were heat treated in between 1200 degrees. The peak approaches to the same value. So from this, student suggested that this peak height position of the peak is a measure of fictive temperature. This is one of the quickest way to measure fictive temperature. As you might know, that glass property depends upon how you heat treat, how you cool. And even if you have the same silica glass, property could vary widely. So it is important to know what was the heat treatment, what was the time and temperature of heat treatment. But nobody is going to tell you. So this way, by measuring the peak position, we can clearly tell what temperature the glass has a fictive temperature at. The important point is this was done by transmission, so entire thickness was being measured. This was measured by reflection, measuring small thickness of the surface. And this suggests to me that the surface layer, which is probed by reflection, is changing more quickly, it's the same time scale, than bulk transmission measurement. And this fictive temperature change is called glass structural relaxation. So immediately we realize this is telling me the surface structure is changing faster than the bulk. This is something new we found, and we measure the relaxation time of silica glass as a function of temperature. Bulk relaxation time is changing this manner. Surface layer changes much faster, smaller relaxation time. And when you make it dry, it's a little bit longer, but far lower than bulk. If you extrapolate to 500 degrees around here, and extrapolate this one, relaxation time difference is 10 to the 8. 8 orders of magnitude faster relaxation at the surface when there's a moisture around. So I thought this must be important because glass properties are affected by surface. Chemical durability, mechanical strength affected by surface. And this must be important. I sensed this is important, but I didn't know what is important for the past 10 years or 15 years. Recently, we did this again 10 years ago. By the way, this is the showing what is the relaxation time. Relaxation time is the speed of structural change or structural relaxation is normally viscosity divided by shear modulus. And the stress relaxation, how quickly stress is removed, is also given by this one, factor of 10 difference. And what we found is surface stress, what we're going to show is the surface stress relaxation also changes faster than bulk. What we did was we took a silica glass fiber and held in silica glass tube and kept at 650 degrees, a couple hours, which is 500 degrees below the glass transition temperature. TG is 1150. So nearly 500 degrees below the glass transition temperature, and then took this out of the tube. Then we found the fiber is permanently bent. And this was observed earlier by other people, but most other people thought this one is the viscous flow. The entire fiber is bending. We felt this couldn't be, so we etched off the surface layer, and then it became straight, showing only the surface is causing this permanent bend. And that must be due to the surface stress relaxation. And one of my postdocs who had a mechanical engineering PhD explained to me this way, that if you have a bending stress, you have a tension and compression uniformly changing across the fiber. When you have a surface relaxation, surface tension is a little bit lost, surface compression is lost, and you let go, then you end up with this funny stress profile. Where the tension was, compression is formed. Where compression was, tension is being formed. And this was again done more than 10 years ago. I still didn't realize until a few years ago this could be important. I'll show you why it's important. And this kinetics of how quickly the bend depend upon how much surface relaxation is happening. So we assume that the surface radius curvature is changing of the thickness Z is affected. The relaxation is happening to the thickness Z. So if you have a cross-section of optical fiber, this is half of the cross-section, surface layer is relaxing. We want simple assumption, step function relaxation, or exponential relaxation, or if it's diffusion, complementary error function relaxation, or straight coming down. So we tried many different profiles, since we don't know for sure, but the equation was almost always the same, that this type of expression can be used. The radius of curvature is determining how much residual stress and how much depth of relaxation happens. And so we did this as a function of time, square root of time, and the change of curvature. Equation suggests that if it's diffusion-controlled process, radius of curvature changes with 1 over square root t. So sure enough, with the experimental error at various different stress, you saw the bending kinetics following the square root of time. So diffusion-controlled process is taking place. And if you normalize the different stress, well, divide by stress, we get superposition of all this data. That suggested to me that the surface layer relaxation is almost instantaneous. So from this type of experiment, we got a diffusion constant called surface stress relaxation diffusion constant. This is again an entirely new concept, that surface is relaxing by diffusion controlled process. Of course, that's water diffusion is related. And we found that as you change the water vapor pressure, higher water vapor pressure has a higher diffusion constant. And you can measure as low as 300 or 400 degrees centigrade for silicon glass. And this made me think, and this was fairly recent, I realized perhaps this surface stress relaxation may be important in glass science and technology. And I thought about 3 years ago, I wrote a proposal to the government. This can be used to make glass stronger. That's one idea. Then I can also explain lots of mysterious phenomena. Over the years, people obtained no explanation. For example, when you do ion exchange, as the Corning does for Gorilla Glass, oftentimes surface compression layer is a little bit sag. And this was observed by many, and Professor Cooper tried to simulate, and his conclusion was it's not possible to simulate the phenomena. Essentially, it's a mystery. Another mystery is when you take a glass, apply a load, strength decreases with time. It's called fatigue. Just like human being, if you have constant flow, the glass gets tired, and then after a certain time it breaks. But if you wait continuously lower stress, there is a limit that how much glass gets weaker. That's called fatigue limit. That again is not known why. Now the first, how can we apply this observation to make glass stronger? You take a fiber, pull. This is the uniformly tensile stress applied. Of course, if you pull too much, it must break. So you do this under subcritical tensile stress. Maybe for optical fiber, you can apply 5 gigapascal. So in this case, we apply 1 gigapascal, 2 gigapascal in air, 200 degrees. And let go. Then the surface stress relaxation happens. That would translate into compression. This was tension, and relax, let go, you get compression. That surface compression formation is the practically useful way to make glass stronger. So I thought this can be used to make glass stronger. Currently there are 2 popular methods to make glass stronger. One is a tempering. Before that, I guess I should say there are, so far I showed there are not so funny effect of water in glass. Some are bad, some are good. Good is good. Good is better. There's a famous comment that I've been poor and been rich. Rich is better. And that's the same way I could say glass has a negative effect and a positive effect. Positive effect is better. So I'd like to show what positive effect glass can have. As I was saying, there are 2 ways to make glass stronger, well known. One is tempering. You take a glass plate to softening temperature, rapidly cool, then glass becomes stronger. That type of strengthened glass is used by your automobile side windows and rear windows. Of course, when you break it, it shatters into pieces because of high energy store. To make such high strength glass by tempering, you have to have 3 millimeter or thicker, because what's happening is a temperature gradient when you're cooling. If you rapidly cool, center portion stays slightly higher temperature than outside, but this is high temperature, so stress is not maintained. There's no stress. And when you keep cooling, this temperature profile continue until room temperature, and there's no stress. Then the center has to cool down to the same temperature to outside. That produces tensile stress. So if you have a very thin specimen, you can't strengthen glass plate by tempering. Second one is by ion exchange. You take a sodium-containing glass like this, and then put in potassium nitrate melt. The potassium is larger, replace the sodium, and that put a high surface compression. That's a very effective way. As I mentioned, the Corning's Gorilla Glass is made by this method. That's why your smartphone is reasonably strong. But that second one, you have to have alkali ion to exchange. First one, you need a thicker sample. The method I'm proposing, are not restricted by this method. I'm hoping this will be third viable method. We can take a glass fiber as thin as 100 micrometer, 125 micrometer, just pull at reasonable temperature, 500 or 200. Then we can heat by putting hot air. And then this is the optical fiber. We remove the plastic coating top and bottom, and only the portion of it was heated. And then we, after holding and cool down, and let go. And then we take that piece and test the mechanical strength. Just to show that a surface compressive stress is generated, we slice the fiber in half. And then because of the compressive layer, fiber should curve in this way. And indeed they do. So we know the compressive stress, residual stress is produced. And by using this treated fiber, we use a two-point bend test. The fiber is bent and compressed. One side is stable, the other side is moving. And when it breaks, the sound is detected, and then we can find out the strain at the time of breakage. And from this type of measurement, we found that the best silica glass optical fiber is 5.51. This is the this is the normal strength of silica glass fiber, the room temperature optical fiber. When you heat it, normally it gets weaker. But when we treat it at 200 degrees, 1, 2, 3 gigapascal, then we got this much high strength fiber. It's 30% higher by simple process. It doesn't take much time in this process. So we definitely demonstrated that glass can be made stronger. By the way, this first author, Peter Ledley, because of this work, he received the Cridle Award given to the best graduate research done last year. And he continued to apply a E-glass fiber. E-glass fiber is used for composite, fiber reinforced composite material to make a stronger material. And people, some high-end composite, they are trying to replace E-glass fiber with graphite or carbon fibers. I'm hoping that this method of strengthening, but this is the original E-glass fiber, after simple treatment, 1 gigapascal tensile stress, 200 degrees, 60 seconds, we can make this stronger. By this method, we just show the method we have not optimized. I'm hoping this would eventually reach to the strength of carbon fibers, so the E-glass fiber, of course, is much cheaper than carbon fibers. So this is one important finding, that surface stress relaxation can make the glass stronger. And the advantage of this method is not limited to the minimum thickness. We don't need a 3 millimeter, but also we can do without any alkali, because the glass composition is irrelevant. And we also did this for soda lime glass. So far we did silica glass, E-glass, and soda lime glass fiber. All can be strengthened. I believe all the oxide glasses can be made stronger by this method. Now this phenomena we found, faster surface stress relaxation, I realized can be also used to explain a couple of mysteries we have known for many years. One mystery, as I mentioned, is if you ionic change, you get normally compressive layer high surface compression coming down, deeper diffusion, ion exchange, with oftentimes surface comes down. Ideally it should go up higher and higher, but surface stress is coming down and it's getting deeper with treatment time at constant temperature. This type of phenomena have been observed for years, but there was no good explanation. What we thought is this must be due to the surface stress relaxation. In other words, small amount of water in the nitrate, potassium nitrate, may be causing the surface stress relaxation. So we plotted this data, the other people's data, plotted in square root t, normalized fashion. And except the very short time, this is the depth of the peak position, and except the short time, which has lots of error, because less than 10 micrometers, they follows a square root time dependency that suggests that's the diffusion phenomena which is causing this surface relaxation. We took the off-the-shelf pure potassium nitrate and we put in thermogravimetric analyzer, and then weight loss was measured as 200 degrees, something is going away. So the molten salt, once you make it molten, it's very difficult to dehydrate. To get rid of water, it's impossible. So we kept the 200 in solid powder and then measure the weight loss. And sure enough, weight loss happens. So I believe water is evaporating from this powder. And using this before and after the heating, we did this fiber bending test I mentioned. Silicon glass fiber was immersed in molten salt and bent, and then took it out to see how much bending took place for given time and temperature. And that is, from that we got the surface stress relaxation diffusion constant of silicon glass. So this one is before drying, after drying. By drying, it dropped. So certainly, whatever it is, we are evaporating. After evaporation, it's happening much less. So water, we believe water vapor is escaping, and that produced this relaxation diffusion constant in molten salt. This was the original silicon glass in air, and this was in molten salt. From this, we can estimate the water vapor in the molten salt is 200 to 300 tall equivalent. Of course, it's not in a vapor form, but there is a small amount of trace of water. So if you'd like to make a better ion exchange glass, one way is to dry the potassium nitrate, make it as water-free as possible. Then you can make even better, higher strength glass. And using this idea, we simulated that incorporating this surface stress relaxation coming by diffusion process, we modeled other people's experiment, and with time we could more or less show the position of the peak is shifting inward and coming down. There are two different mathematical models used, and both capture the essential features of experimental observation. So I believe we solved this mystery of why the surface compression of ion exchange glass going down. And this was published this year in Journal of Sensory. The other mystery in this field is this fatigue. As I mentioned, glass, if you apply a constant load, and it would not break instantaneously, but after a certain time, glass will break. That's just like human being, glass getting tired. And that normally is related to the moisture effect, water effect. And this shows the logarithmic time scale. This requires great patience to do this experiment. This is soda lime glass in water, tested, initially stronger short time, weaker, and this is roughly 1 year. So this type of experiment is very valuable, but it's not appropriate as a PhD thesis. One gets very old by the time you finish this research. So this has been available, and why this happens, even though it's coming down, but it starts to saturate, and that's a very good thing, that if you apply this load, it will never break. As long as you stay below this load, that product can be used for years to come. That's very important if you are trying to use optical fibers or solar panel meant to be used 30, 40 years. Would the glass survive that period? That's a very important question. And this observation of fatigue limit is, in a way, is a saving many manufacturers. But the question why this happened is not known. And I believe this one is also due to surface stress relaxation. Under stress, there's a near crack tip, there's a high stress, tensile stress, but the moisture around come in slowly and stress relax. So that tensile stress near the crack tip is reduced, especially long time that can happen. And when that balances, when the relaxation wins out over and against the applied tensile stress, no fracture will happen. So first we thought, oh, this must be surface stress relaxation. By the way, there are lots of other people suggested different theories, but nobody seems to agree with each other. So we came up with this idea, perhaps we could explain. This somewhat related phenomenon to the fatigue is the slow crack growth. This was pioneered by Sherry Winnehorn and his collaborator and NIST in late 60s, 70s. They measured a variety of different glasses and applied stress, what stress intensity to be precise, as a function, the crack growth rate as a function of stress intensity. If you apply higher stress, of course, crack grows faster. So they normally have this slope. And this is highly sensitive. This was promoted by moisture. In this case, it was done in water. I believe this one is also water. So water is causing this. If you do air, that happens slightly slower but similar trend. What is interesting is that the crack growth logarithmic to stress intensity normally linear. But if you go down, 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 it starts to come down, drop faster. So this corresponds, somewhere around here, corresponds to fatigue limit. Below the stress intensity, crack growth wouldn't happen. So this must be caused by surface stress relaxation. That was our conjecture. And so this is the three glasses: sodium, potassium, lithium, aluminum, silicate glass. Potassium glass seems to have a higher crack growth than lithium, but also tend to stop at higher stress level. Around here, no more crack growth. Lithium around here, the sodium glass here, lithium glass around here. Soda lime glass shows this. Silica glass has not shown any bend like this. So you have to go to long time, or patiently very long time, slow crack growth, or you go to higher temperature to see the phenomenon. So we took those three glasses, potassium, sodium, lithium, and we bent and measured bending kinetics, how quickly we bend. This potassium glass, this is the radius curvature small, means bending faster. And sodium is next, and lithium was least. And they have a different modulus value, so we normalize to constant modulus, multiplying modulus, still the trend consistent. That potassium glass has a faster surface stress relaxation, and that glass is the fastest, or they show the fatigue limit under higher stress intensity. So qualitatively, we think we are in the right track. And this trend can be shown in this manner. This is the more bent with under constant temperature, constant time in water, potassium glass bent most, sodium next, lithium next. And that we plotted evaluated surface stress relaxation, diffusion constant, this is the highest diffusion constant, and the stress intensity below which crack growth comes down precipitously, and they seem to correlate. And this one is the soda lime glass, three different temperatures, the similar parameter shows this. But of course, they are comparing different features. This is the glass type. This was temperature effect, so we don't expect a line on the same line, but trend is always the same. Higher surface stress relaxation diffusion constant, then higher stress intensity crack growth stoppage. So this qualitatively support the guess that fatigue limit is caused by the surface stress relaxation. So this, we did more quantitatively, and that's the reason, the reason we can do is I'm collaborating with mechanical engineers. And then this related work was done by Michalski, also happened to be our Alfred graduate way back. He was expert on mechanical properties, and he did interesting thing. He took glass, soda lime glass, kept around here. It's coming down quickly. Very slow crack growth. Crack growth is negligible around here. So he took this glass and held around here certain time, 16 hours at this point, around this point, and then brought to higher stress intensity. And then he found the funny thing that if you go to here, you have to wait a long time before the crack restarts. If you go to higher value, it started more quickly. So by the treatment here, this wait time was observed. That's, again, is a mysterious phenomenon nobody can explain. But we think this, while holding here the glass experience surface stress relaxation. You are applying small tensile stress. At the crack tip, there is high stress, and the water vapor is slowly affecting that stress profile. And that, when you let go, produces compressive stress. So this, in collaboration with mechanical engineer, this is the normal expression. When you apply uniform stress, there's a high stress on crack tip. And that looks like this. Very high stress. This is the infinity. And this is the crack tip. And this is extremely high stress unless there's a plastic deformation. Now, if you hold that lower K value, this crack will not grow, or very little growth. And then there's a moisture effect. That stress is relaxing. This is with time goes this way, this way. This is the diffusion control. So that would be propagating square root of time. And that would produce the force, that part would suddenly affect the crack propagation. And that part we can analyze in this manner, that there is original tensile stress, but relaxation reduces this, and that we can superimpose as a compressive stress. The relaxation produces effectively compressive stress. So we have to deal with this far stress field and the local stress due to compression. And that has an effect on shielding the crack growth. And that idea has been used in some other materials, such as transformation tackling of ceramics. And more recently, the Wilhelm thought water diffusion itself is making an expanded swelling region that mitigate the applied tensile stress. So we use the similar mathematical formula. Normally, in general, stress intensity is a function of applied local stress and weight function. This is the mechanical engineer's realm, so I have to accept what they say. The weight function is given as long as you have a particular shape of the crack tip. And then we have the compression due to diffusion control process. This is a complementary error function, diffusion control process. So that is the changing the field. And that is the result of crack shielding, is superimposed due to surface stress relaxation. This is the amount of shielding calculated. Crack tip is here, and with time, the shielding is propagating deeper, deeper into the glass, ahead of crack tip. So when you apply crack, the tension, there's a high positive stress intensity, but at this point, there's a large, equally large opposite side. There's not much stress here. So that when the crack propagates here, it will take a long time at this point because the stress is very low. In other words, this is shielding effect. So the velocity of the crack, we assume that the original crack growth line stays linear, ideal case, if there is no shielding. But we have to introduce shielding, and therefore it will take time to propagate in this region where there's shielding stress intensity. So crack growth is very small. By the way, this is such a small scale, 10 to the minus 10, that's 1 angstrom scale. So this 10 angstrom, it's a very short distance. Crack growth is very difficult, slowly growing, but it takes time. So we can calculate how long does it take to go through, and then we came up with this result, that if you apply lower stress, you have to wait a long time to pass through this shielding region. So it will, low stress, high stress, it can go up very quickly. This, after passing the shielding region, normal crack growth starts. So that's exactly what has been observed by Michalski, and some years later, German scientists, as well as Wilhelm, reproduced this result. So this is our simulation, so they are matching reasonably well. So we feel we have solved the second mystery of the glass strength in terms of surface stress relaxation. So in conclusion, I can say the trace amount of water in atmosphere causes a faster surface stress relaxation than bulk stress relaxation. The surface stress relaxation concept has not been recognized, not discussed, so I don't think you'll find it in Web of Science. And we found this can apply to make a stronger glasses, and that method is applicable to all kinds of glasses, not limited to the thickness. Finite thickness is not needed, just like as in tempering, or we don't need ions to ion exchange. Any oxide glass can be strengthened by this method. Even if you have a large bar, as long as you have enough machine to pull, you can make the glass stronger. At the same time, this method, faster surface stress relaxation, can explain various mysteries known in glass science community. One of them is the surface maximum, the surface compressive stress made by ion changes sliding. And that can be explained by surface stress relaxation. The second one is a fatigue limit, can be accounted for by using the idea of surface stress relaxation. And that is the, at least the fruits we have obtained. Whether it's sweet or sour, we shall see. So that's my conclusion, and I appreciate your attention.
I now welcome the audience to ask questions. For Professor Tomozawa, please feel free to raise your hands.
Can you light up? Can someone switch on the light? So I'd like to be able to see the people I'm talking to. Okay. Yes, please. That, as I was saying at the end, all depends on how much machine you, how strong machine you have. Even if you have a 5 millimeter rod, as long as you can pull the bar below the maximum the breaking strength, you can go as high as the glass bears, or even bending also. And then that much of applied stress approximately has added up as a compressive stress. So in principle, we haven't demonstrated large bar, but in my opinion, even in sheet willow glass or corning, maybe put two-dimensionally, make longer. So I think all the limitation is your imagination. Yes, please. Yeah, this one is after applying to NSF, funded nearly 2 years ago. So 2 years was enough to demonstrate our ideas and applicability to solve mystery. That part is a very interesting question. How do you apply? And at the moment, we haven't done any beyond 100 micrometers fiber. But one of my colleagues, I gave this talk internally, and one of my colleagues worked on composite material, e-glass fibers and carbon fiber. Price of carbon fiber is far, far greater than e-glass fiber. So if you could make e-glass fiber close to carbon fiber, that would be great. So he has a machine to do this, so I'd like to try see what happens. We have not reached the ultimate. We just did preliminary test, but demonstrated the feasibility For example, if you have 5 gigapascal strength fiber, you add 2 gigapascal by pulling, that's 7 gigapascal. Then you can apply 6 gigapascal or even higher value. Where incrementally you can increase. And in my mind, there's no limit. Only limit is when you have a surface compression, there must be surface, interior tension. So it will continue until such time the surface stress, tensile stress becomes a bond strength, at least in principle. So that's, I feel very optimistic until proven wrong.
We can continue having dialogue with Professor Tomozawa, and I understand some of you have to get back to your classes. Let me appreciate you all for coming. Thank you so much, but please feel free to stay and have dialogue with Professor Tomozawa with your questions. He will be here for a few more minutes before we head out for lunch. Thank you again. Any other questions for Professor Tomozawa? All right, you're welcome to come and also introduce yourself and talk to him. He'll be here for a few more minutes. Thank you.